is the first visualization in a series of visualizations that illustrates the importance of finding representations when making classifications. And in this first video, my goal here is to demonstrate the motivation. Why do we need to learn representations in order to make classification? So to begin with, here we have the logistic regression function that has parameters that we can control, and it's our goal to find these parameters for the logistic regression that will parameterize the logistic regression in such a manner that it will discriminate between the classes. And we can try to find these parameters manually using these sliders, or we can just click on the step button and it will make a gradient descent step for us. Hopefully, we will end up with parameters for the logistic regression that parameterize the logistic regression in such a way that it discriminates between the classes well. So, in this case, we don't need to use any representation since the data is so simple and linearly separable. So we can just fit the logistic regression model to the data as is and get the desired result. Unfortunately, most of the time the data will not be so simple and linearly separable. For example, in this case, there is no line discriminate between the classes, so it doesn't matter how long we try to fit the logistic regression model to the data, the training is obviously going to fail. So, in conclusion, we cannot use the logistic regression model on this data as it is, since the data is not linearly separable. But if we still wish to use a logistic regression model, we must somehow find a representation of the data where in that representation the data will be linear, the classes will be linearly separable, and then we can try to fit a logistic regression model not on the raw data set, but on a representation of the data. So it sounds complicated, and it is, but fortunately we have a machine, good machine, that knows how to take data and find a useful representation of the data for downstream tasks, which in our case is to discriminate between the classes. And this machine is called a neural network, and we will see how neural networks helps us to find good representations. So our goal here is to demonstrate how the transformation occurs in neural network parameterized with some arbitrary parameters. However, in the next visualization, we will combine this visualization with the previous one of the logistic regression to examine how neural networks can learn these parameters for the transformation from beginning to end. So we have here a very small neural network that transforms the input space into a representation space based on the parameters that we give here, and it's our goal to find parameters for this little neural network that define transformation of the data into new disentangled linearly separable representation. And we can see here, for example, the numbers here in the input neurons corresponds to this specific point, and we can see where each point is transformed in the representation space, but we can also see how the transformation, how all the plane transformed during the transformation, how all the input space transformed, and we can, let's look run like that. And one thing to note here is that we have to use non-linear activation function in order to get good representation, since if we will just use the linear activation function, this is equivalent to just linear transformation of the input space, and because we know linear transformation keeps lines between the input space and the output space, so there is no way that now in the output space there was a line that discriminates between the classes. Since if there was a line that discriminates between the classes, this means that there was a line also in the input space that discriminates between the classes. But if there was a line in the input space that discriminates between the classes, we didn't need to find any representation from the beginning. So we have to use this non-linear activation function. And as I say, now our goal is to find these parameters for the network that will define transformation to new representation of the data. So this is the combined visualization, and the first part of the network is the same as in the previous visualization. We have here the small neural network that maps this two-dimensional input space into a two-dimensional representation space, which now is on the plane here. But now we also include this last neuron, which operates as a logistic regression, as we saw in the first visualization. However, the difference now is that the logistic regression no longer works on the raw input space where it fails to discriminate between the classes, but on the representation found by this little neural network. So we can view this network as containing two parts. The first part tries to make better and better representation, namely representations where the data is linearly separable, and the logistic regression part in turn comes and tries to discriminate between the classes, but in this new representation, not on the raw input space. And consequently, if the logistic regression fails to discriminate between the classes, it not only changes its own parameters, but sends error signals to the first part, causing the first part to make better and better representation, and makes the first part causing the transform to representation where the data is more disentangled and more linearly separable. So we can see it. We actually see that the data, the first part tries to transform the input space in such a way that it's like take the red points and discriminate them from the blue points. So now the logistic regression can come and discriminate between the data in that new representation.